Hi there, Rachel Chase here, and in this video we're going to explore discrete probability distributions. Probability distributions are a branch of probability that give you a comprehensive list of anything that could happen and the likelihood that it occurs. So if you think back to frequency distributions, it was the frequency as opposed to the relative frequency, which would have been the probability. So it's a comprehensive list, including the probabilities. Now, one of the requirements of a probability distribution is that you have all pieces of data. So if you're dealing with, for example, a discrete probability distribution, which is what we'll focus on in this chapter, then it would have to be a finite list of things that could occur. A random variable is defined as whatever piece you are investigating as you go. For example, so we said defined as the piece of interest, if you will. So if you think about flipping a coin, let's say you flip that coin 3 times, if you're curious as to how many times the tails appear, then that would be your random variable. Random variables can be either discrete or continuous. Discrete meaning, if you think back to chapter 1, so that would be a finite number of values. And of course, continuous meaning infinitely many values. In our next chapter together, we will explore continuous probability, but for now we're going to focus on discrete probability. A couple conditions for probability distributions is, for starters, you have to have all of your data, so that means the sum of the entire distribution, so the sum of your p of x's, have to equal exactly 1. They cannot be more than 1, they cannot be less than 1, but a total of 1. You can have no negative probability, and also you cannot have any probability greater than 1. So remember that each individual probability has to be between 0 and 1, and the sum of that distribution must equal exactly 1. Let's take a look at a few examples. Determine if each of the following is a probability distribution. So let's check it based on those 3 requirements. A survey is conducted to determine the number of siblings respondents have. The results are as follows. So we have the respondents at either 0, 1, or 2, or 3, and the respective probabilities. So the first thing we have to check is, do the probabilities add up to exactly 1? So we have 25, 50, 85, 100 when we add that up. So that is a total of 1. So that's good for us, right? The sum of the probabilities equal 1. Also, we have to verify in here, are any of these greater than 1 or are any of them negative, which means less than 0? And in this case, those do not apply. We have nothing greater than 1 or less than 1. So we can say that yes, this is a probability distribution. How about this example here? A weighted or biased coin is flipped 3 times. The probability distribution below represents the number of heads which appear on that weighted coin. So when you flip the coin 3 times, there can be anywhere between 0 and 3 heads appear. If we take the sum of this column, we have 25, 50 plus another 55, that's 105 minus 5. So that does actually add up to 1. However, what breaks this? The fact that the probability of 3 heads appearing is a negative value on here, that is something that's impossible. You cannot have negative probability. So this time we can say that this is not a probability distribution. Let's go ahead and learn how to construct our own probability distribution. For the next example, construct a probability distribution for the number of male children in a family with 4 kids. Now, one thing you want to consider doing first is taking a few minutes and writing out what the sample space looks like. If you have the full list in your sample space, it does make this a little bit easier. Now, as you may recall from our class time together, we talked about using tree diagrams to construct our probability or to construct our sample space. So in a moment, you'll see here a tree diagram which represents the sample space. So this tree diagram represents what our sample space would look like. Now it's up to us to follow the branches to collect the list of the sample space. This will make it much easier for constructing our probability distribution. So if we follow the first one here, we have male, 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 male. And then we'll repeat this process for all other of these 16 total branches. This list here shows us all 16 possibilities that can occur when a family has 4 children in terms of the gender outcomes. So now the question is, if a family has 4 children, how many different ways could there be male children? We could have either 0 male children, or maybe 1, or 2, 3, or at most 4. So all of those are a possibility. So to construct our probability distribution, X is going to equal the number of male children in the family, and then P of X will be the probability that that situation occurs. So we said that we could either have 0 males, 1, 2, 3, or 4. And what we're going to do here is start by counting up the ways that can occur. The only way for there to be 0 males in a family is for all of them to be females. So the probability of that is 1 out of 16. How many ways, we'll also do the other simple one, can you have 4 males in a family? It's only when they are all boys. So again, the probability of that is also 1 out of 16. Next, let's look at the number of ways to have exactly 1 male child in a family. So we're going to scroll through our list here and make a note anytime only one M appears. So it would be here, 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 and here, which is 4 out of 16, or reduced, that is 1/4. Then we'll repeat that for 3 males. 3 males means only 1 female. So that would be here, here, then we have here, and also here. So also 4 out of 16, which is 1/4. So how could you find the number of times 2 males appear? You can go back to your list and count it up, or you can use the complement rule to fill this in as a shout out back to chapter 4. How much does all of this add up to? We have 5, 9, 10, which means that there are 6 remaining out of 16, which reduces to 3/8. So how could you verify that? Go back in here and count up the ones that were not considered. Now, although this next trick won't tell us if we've done something wrong necessarily, it will point out a red flag if we've definitely made a counting mistake. If we add this up, because it's a probability distribution, the sum has to equal 1, which if we run down, the total is 16 out of 16, which reduces to 1. We also know it's a probability distribution because this is a comprehensive list of everything that could happen and the likelihood that it occurs. As with much of what we have done this semester, something that comes in handy is being able to calculate the mean and standard deviation for a set of data. So let's talk about how you would calculate the mean and standard deviation of probability distributions. The mean has another name that's significant to us, and that is also known as the expected value. So those two things are used interchangeably. To calculate the mean, the formula is mu equals the sum of x times p of x, which, if you think about it, this is the exact same formula as the weighted mean, only said a little bit differently, because you're taking p of x, which previously has been known as the relative frequency, and you're applying it to some type of distribution. So in the past, you used to multiply your values times their frequencies and then divide by n at the end. Now, since everything is divided by n as we go, it's one less step, right? So you don't have to divide by n, you just multiply and add things up. So we've already used this formula in one way. It's also a population mean because any distribution has to be a comprehensive list, so it's implied that that is population data. The formula for standard deviation is the square root of the sum of x minus mu squared times p of x, which also is just a variation of the grouped standard deviation formulas we've used in the past. And of course, the variance is the same formula as our standard deviation without the square root. So just the sum of x minus mu squared times p of x. So whatever method you like to use, whether it's using the list functions in the calculator or even one var stats, both of those will produce the same results if you're using that to calculate your answer. So let's take a look at an example at calculating these. Consider the probability distribution of the gender of male children with a family of 4 kids. How many kids would you expect to find in a family of 4 kids? This is asking for the mean. And then what is the variance and standard deviation? So let's take a moment and using the data that we already found on our previous example, go ahead and continue the calculations for finding the mean and standard deviation. If you would like to follow along with these calculations in the graphing calculator, please see the right side of the screen here. We're going to start by entering our probability distribution, and we'll have on the first the x values, this will be in list 1, p of x will be put into list 2. This is the way that you can use the calculator similar to Excel to show you the work for you so you don't have to calculate each individually. I'm going to start by entering these values. So we have 0, 1, 2, 3, and 4. In p of x, it's going to convert these into decimals, but that's okay. We have 1/16, 4/16, 6/16, 4/16 again, and 1/16. If my first column for finding the mean, remember mu is equal to the sum of x p of x, is to multiply, I'm going to create a column for x times p of x, and I'll put this in list 3. So in my calculator, I'm going to highlight list 3 up at the top and tell it to take list 1 and multiply by list 2. This then are the multiplied values, and I can just copy those as is. So we have 0, 0.25, 0.75, 0.75, and 0.25. Add this column up. When we add this up, we get mu equals 2, because that's the total, right? 0.75 is 1.5 plus another 0.5. Now, does that make sense in context? Well, if you have 4 kids, in theory, it's a 50-50 chance if you're going to have boys or girls. So would it make sense that 2 of your 4 kids are males? Absolutely. So this follows with what we would normally expect. To finish off our calculations for standard deviation and variance, in list 4, or my next column, I'm going to calculate x minus mu. Since my x values are in list 1, I'm going to tell it to take list 1 and subtract my mean that I just found of 2. And copy this list over. We have -2, -1, 0, 1, and 2. And then similarly in list 5, I know these are simple calculations, but if you had more advanced numbers, you would want to run through this with a calculator probably. I'm going to take each of those and square them. So in list 5, I'm going to say take everything in list 4 and raise it to the second power. And last but not least, because of the probabilities, we have to weight our data by each probability. So list 6 is going to take each of those squared values and multiply by p of x. So that is my 5th list times my my probabilities are in list 2. So that gives us 0.25, 0.25, 0, 0.25, and 0.25 again. My variance is equal to the sum of this column, which is 1. So I have a variance, sigma squared, equal to 1. And my standard deviation is the square root of that number, which in this case is also 1. That is completely coincidental and will not happen in every single probability distribution, so that's something to keep in mind. But in this case, our variance is 1, our standard deviation is 1. Now, let's say that you wanted to use one var stats for something like this. You absolutely can. Our data is still in list 1 and list 2. If we go to stat, calculate, one var stat, we tell it our data is in list 1. And instead of a frequency list, it's our probabilities, but that's in list 2. So we go and press calculate. And what you'll notice here is that it doesn't give us a sample standard deviation to pick between, because when probabilities are in there, it recognizes that this is a probability distribution. So the only thing we do have to be mindful of when we're checking that is that the symbol that they give for mean is referring to a sample mean instead. So just make sure that you recognize that even though it says X bar, that is actually the population mean for something like this. Let's take a look at one more example and at least set it up, and then we can use one of our stats to run our calculations. A certain lotto game costs $5 to purchase a ticket. 80% of players will win nothing. In other words, they're going to lose $5 because they had to pay that to play. 15% of players will win $5, so they'll actually break even. And 5% of players will win $50. Construct this probability distribution. How much are they expected to have in net winnings? Would you want to play this game? So it's a couple of loaded questions here. Well, for starters, what is our random variable? X is equal to the amount of dollars of net winnings. And then we're going to find the probability of each of those occurring, respectively. So if somebody pays $5 to play and they lose, that means they lost $5. If they win $5, it means they've broken even. And if they win $50, it means they've actually only net gained $45. They told us the probability that somebody loses is 80%. The probability that they break even is 15%, and that they win $50 is 5%. So if you wanted to use the calculator to complete these, you go ahead and enter your data in list 1 and list 2, and either use the steps on the previous example, or go ahead and use one of our stats, which is what we'll do here. Now that our data is entered into L1 and L2, I'm going to go under Stat, Calculate, one of our stats. Make sure your list and frequency are correct, and then press Calculate. So this tells us that we would have a mean. In other words, you could expect to, it's negative, so that means expect to lose $1.75, and a standard deviation of $10.87. So what's the catch here? The catch is that if you play this only one time, you're not going to necessarily lose $1.75. But this means that in the long run, if you kept playing this game over and over and over again, eventually it would even out to about a loss of $1.75. So the question, would you want to play this game? That's entirely up to you. Generally, if you're losing money, you probably wouldn't, but if you see it as enjoyment, you might want to, right? So the disclaimer is this is not an encouragement to gamble, but just an explanation of how one of these lottery games might work. Thanks for watching. In the next video, we will take a look at specifically binomial probability distributions. See you there.